Sean Awago, and I'm with Scholars Academy at the University of Houston downtown. Now, here at the Scholars Academy, we believe in outreach to the community, and as we are an organization focused on promoting STEM and STEM career pathways, we, in fulfilling that goal, do what are called service learning projects, where we go out into the community and raise awareness about STEM, about different career paths related to it, in order to give the community an idea of what STEM can be and make it personable. Now, this year, due to restrictions related to COVID, we've decided to focus on at-home experiments. So, in line with that, I will be giving an outline of our members' experiments. Now, performing the crystallization experiment will be Aaron Torres, Laura Conde Puello, and Jeff Kayaks. Performing a cabbage pH indicator experiment will be Araceli Garza and Taylor Newton. Performing an extraction of potassium carbonate from the NIMS will be Vincent and Nick Huyn. Performing a cornstarch slime experiment will be Karina Rodarte. And finally, performing a turmeric pH indicator experiment will be Angela Vasquez. Now, let's move on to the experiments.
Hello everybody, my name is Aaron. I'm from the University of Houston downtown, and today we're going to talk about making a variety of alum crystals. We are going to discuss the vocabulary to use in this presentation. Solute is the majority liquid content. Crystalline is a crystal-like structure. The decahydrate is 12 molecules of water. Nucleation is the appearance of a crystalline phase from either a supercooled liquid or a supersaturated solvent. The second step is known as crystal growth, which is the increase in the size of particles and leads to the crystal state. Saturated solution is required to make a crystal. It is a mixture of a solid and liquid component that make up a homogeneous in appearance mixture. The solution made is unsaturated because it has not dissolved enough solid to become saturated, which at that point, when the solid has stopped dissolving in the allocated amount of solute, the solution has reached a saturated point. Visually, it is observed that the solid is pounding on the bottom of the saturated solution. In this experiment, we are using McCormick alum, which you can find in your local food stores in the spice section. It is a firming agent. It is a potassium aluminum sulfate, predominantly made in the decahydrate form, and the solubility is 25 grams in 100 milliliters of water in the 60 degrees Celsius. It is also known as potash alum. There are various types of alum: potash alum, soda alum, ammonium alum, chrome alum, selenium alum, and the uses of alum are used for purification of drinking water, used as a chemical flocculant, mirror response trigger, ingredients in some types of toothpaste, flame retardant, acidic component for baking soda, and modeling clay. In this experiment, we used about 25.53 grams, and to the picture on the left, you can see the alum surrounded by 12 molecules of water, and that's what takes up the lattice crystal structure. On the graph to the left, you can see concentration times temperature graph, and it can tell you that they're at an unstable zone. You'll get spontaneous nucleation, which results in small crystals. The metastable zone is what actually has a larger crystal growth lattice, and stable zone you have no crystals at all. The materials used in this experiment are distilled water, alum, cup, filtered paper, funnel, graduated cylinder, 2 petri dishes, a scale, a yarn, a thermometer, camera, a heat source, a spoon, and some soap. So in this experiment, you had to dissolve alum into 100 milliliters of hot water, which is 60 degrees Celsius, until the saturated point. Filter the saturated alum solution and place 50 milliliters of saturated alum solution into 2 dishes. place one in the house and the other one in the garage and observe it in intervals. Store the crystal seeds to maintain them before the experiment so that when they dry up you can tie them up on a yarn and put it in, repeat the steps of making a saturated solution and storing it so that the crystal seed can grow larger. These are some pictures of the procedures. Some things to consider: temperature of the water, total mass of atom in the container, saturation point mass, crystal seed size, crystal seed quality, and crystal seed growth. I placed 2 petri dishes in different locations. One of them was at the house and the other one was stored at the garage. The crystals stored in the house grew chunky and spaced out. There was a mixture of foggy and clear seeds, and the liquid did not fully evaporate, but you can just pick out one of the seeds and dry them on acetone, or if you have any nail polish around from anybody in your house. The crystals stored in the garage grew small and crowded. Majority of the crystals are clear, and the solution did not fully evaporate. It actually collected a lot more liquid because it was humid. It was a humid weather where it was stored at. And if you collect 10 crystals and redo the procedure, put them on a new saturated solution, they will grow larger. And usually you will want to do this because you pick the most clear small crystals, you place them on a new solution, and they grow larger and clearer, which increases the purity of the potash alum that you're collecting. That is because the potash alum on the McCormick brand contains an anti-caking agent so that it does not collect moisture over time. So that's an impurity already present in the McCormick alum itself.
Seeding and Alum Crystals by Yaura Condepuello. Background on seeding. Seeding has become one of the most critical steps in optimizing crystallization behavior, process efficiency, and product quality. Inconsistent filtration rates, drying times, yield, bulk density, flow properties, and particle size distribution can often be traced back to inconsistent seeding and nucleation. Many parameters must be taken into consideration when designing a seeding strategy, such as seed size, seed loading, and seed addition temperature. In very basic or simple terms, seed particles are added to replace nuclei particles that would otherwise be created through spontaneous nucleation. The seed particles provide the surface on which a dissolved solute can grow. For example, if 1,000 seed particles were added, it would be expected to have 1,000 particles at the end of the crystallization process. These particles would, of course, by this time be larger in size. Now, in reality, the nucleation process, which is a function of supersaturation as is particle growth, can never be fully quenched. For example, see Figure 1. Therefore, there will always be some level of nucleation even in the presence of seed particles. The level of nucleation is a function of the rate of the supersaturation generation during the process and becomes a critical parameter that must be optimized with the seeding step itself. So here on the left-hand side, I have a plot showing the relationship between the supersaturation growth and nucleation rate. What is a seed crystal? A seed crystal is a small piece of single crystal or polycrystal, such in my case material, made from which a large crystal of the same material typically is to be grown. The large crystal can be grown by dipping the seed into a supersaturated solution, or in my case, a saturated solution, into molten material that is then cooled, or by growth on the seed faced by passing vapor of the material to be grown over it. Now, the theory behind this effect is thought to derive from the physical intermolecular interaction that occurs between compounds in a saturated solution or possibly vapor, and a solution liberated with molecules that are free to move in random flow. This random flow actually permits for the possibility of 2 or more molecular compounds to interact, and this interaction can actually have intermolecular forces between the separate molecules and form a basis for the crystal lattice. Now, this placement of a seed crystal into a solution allows for the recrystallization process to happen quicker by eliminating the need for random molecular collision interaction. Now, by introducing this preformed basis of the target crystal to act upon, the intermolecular interactions are formed much more easily instead of relying on random flow or Often this phase transition from a solute into a solution to a crystal lattice will be referred as nucleation. Now, seeding is therefore said to decrease the necessary amount of time needed for nucleation to occur in a recrystallization process. Now, if you take a look here at the left-hand side, I have a solubility curve and an MZW metastable zone width, which I'm going to explain. So having decided that a process should be seeded, the next step is actually to identify at what temperature or what point the seed should be added. Now, this is where the solubility or the MSZW metastable zone width data can be a significant benefit. Now, a rule would be to add the seed particles midway between the solubility curve and the metastable zone. Now, one consideration that needs to be taken into account, especially when scaling up, is that solubility is a thermodynamic function and is scale independent. The MSZ, on the other hand, is a kinetic function which is a scale dependent and is influenced by the rate of supersaturation, generation, mass transfer, heat transfer, and the presence of solids or impurities. Now, it should also be noted that dissolved impurities can actually have a significant effect on the solubility. So the procedure. So it was a stock solution of saturated aluminum, which was added to 2 petri dishes, and one petri dish had a crystal at the bottom, and the other petri dish had a crystal attached to the string. So it had one nucleation site versus many nucleation sites. So that's what I was trying to test in this experiment. So here I provided pictures of crystals every couple of hours at 25 degrees Celsius. So here on the right-hand side, we can see data taken from an MIT experiment in which the data is for an inorganic compound being crystallized from water. Now, cooling is at a fixed linear rate, and figure 2a shows an MSZW of 15 degrees Celsius when cooling perfectly clean particle-free solution. In the case of figure 2b, 10 large crystals were added, which weighed less than 0.001 gram, were added to the point of saturation, and the point of nucleation in this case was detected 6 degrees Celsius earlier than that observed for the figure 2a, resulting in an MSZW of 9 degrees Celsius as compared to 15 degrees Celsius. In this case, the presence of only a few seed crystals has significantly narrowed down the MSZW. So my conclusion was that seeding decreases the time for crystal formation, and more nucleation sites allow for faster crystallization, which backs up the data that MIT had, because what I saw was in my first experiment where I had no seeds, the rate for the crystals to form was much longer as compared to this experiment where the crystals formed almost in the same exact day. So it does confirm that crystals do speed up the process. And that's the end of my presentation. Thank you.
Hi everybody, my name is Jeff Kayaks, and today we're going to talk about crystallization, but in crystallization of sodium chloride, also known as table salt, and my colleagues talked about crystallization of aluminum. So let's get into it. So what is crystal in terms of chemistry, right? So we hear crystals, and every time we talk about crystals, we think about something that looks like this in the upper right hand side. Those uniform structures, right, that are glass looking. And the reason they're called crystals in terms of chemistry is due to the structure. And then chemistry, there's a major topic or a major branch focused on the study of structures. And in terms of solids have something called crystalline structures or crystalline forms or amorphous structures, right? So if they have a crystalline structure, they will be called a crystalline solid. And if they have an amorphous structure, they'll be considered an amorphous solid. And solids that have a crystalline structure, as you can see, have a more uniform structure. So it's just a repeating pattern of atoms, and that's what gives them that unique, uniform, crystal-looking structure that we normally associate with crystals, and that's how crystals get their name. In terms of amorphous solids, they have more of a random arrangement in terms of atoms and the macroscopic level. And the macroscopic level meaning our normal size, what we can perceive. So when we see them, it's just solids that look very dull or not really interesting. So we'll get to the point why crystals are expensive in terms of chemistry, and why they have a crystalline structure in nature opposed to a amorphous structure. So a little bit more of the background. So when we're going to talk about dissolving and building crystals, right? So we're going to view them as dissolving is the opposite of forming a crystal, and crystal is the opposite of dissolving, right? And that's what it really is. So as you can see here in the lower right hand corner, we have this chunk, and as it's going from the chunk from the left to the right, these water molecules are taking apart the chunk and surrounding it by water molecules, and that's called hydration. And it gets to the point where enough water molecules, so 6 water molecules per each ion, positive or negative. So the negative ions are going to be the chloride part of the sodium chloride, and the positive ions are going to be the sodium part. The chloride is negatively charged, and the sodium is positively charged, and they're going to have 6 water molecules surrounding them. And when, as you can see right here, and when the water is uniformly, when it reaches a homogeneous level, where there's going to be equal parts water and equal parts chloride surrounding it, then at that point it's going to be saturated. So we're going to talk about unsaturated solution, saturated solution, and supersaturated solution, which I'm sure you've heard in your science classes, right? So we're going to relate that to those terms. So your unsaturated solution, we know that more solvent, more of the solute or sodium chloride can be dissolved in it. And in terms of the saturated solution, we know that that's the maximum capacity where no more salt can be dissolved in the water. And supersaturated solution is where when the solvent, again water, is over its maximum capacity to dissolve salt, and that's when you see pieces of solid salt just depositing at the bottom of your container, right? So what happens in an unsaturated solution is that there's still water molecules left that can associate with either chloride ion, aka the or alias the negative charged atom, and the sodium atom, which is the positively charged. So you have water molecules left to surround them, right? Once you if you keep on pouring more salt, then you're gonna run out of water molecules to surround each negative or positive ion, that it starts to kind of just rejecting them, because at that point the water cannot be uniformly, so it's no longer a homogeneous solution, so it starts rejecting. And when it's rejecting all those ions, it's gonna accumulate them at a single spot, as you can see here. So you can interpret this picture as dissolving, or you can interpret it as forming a crystal, which these are being deposited one by one, and that's how you build a crystal. So once you're supersaturated, then the water itself is gonna place the atoms in the correct positions, one by, like, very slowly, and it will make the uniform structures that will result in a crystalline structure, right? And here we are, a picture of what I was talking about. So in this picture, we can either associate the water molecules hydrating each ion and dissolving the bigger part away. So these water molecules are associated with each ion. See, so 6 for the positive and 6 for the negative, and taking it away and making this bigger structure smaller and smaller until everything is dissolved, right? So we can also interpret it as the water molecules building the structure, so they're gonna uniformly put the atoms back in place, right? Depending if they reach their maximum capacity, which it doesn't look like because there's still some free atoms, some free water molecules. But if there wasn't, if these were all associated with the ions, then that'll be more of the case. But we can just pretend that all the water molecules are associated with an ion, so that's why they're depositing each ion back into place in a uniform structure, and that's how you make your crystal. So, and that's when we can manipulate solubility of the solution, and we're gonna get more into that. So this chart right here, so our procedures are based on this chart. So we can see this line that's very curvy and kind of a straight line, right? So the curvy line represents the solubility change of sugar as the temperature is increased in terms of grams per 100 milliliters of water, right? So for each 100 milliliters of water, this is the amount of sugar that can be dissolved as temperature increases or decreases. So as temperature decreases, less sugar can be dissolved in the water. So how can we use this for our procedures? So in terms of salt, it almost looks like a straight line, but it actually isn't. And this is one of the downgrades of using salt or table salt, sodium chloride, as a crystal material, because it doesn't have very good solubility. See, compared with sugar has a greater solubility properties compared to salt. When the temperature is being raised at the same rate, sugar solubility increases dramatically. However, salts stay almost the same. So this is why when we want to build a crystal with sodium chloride, it will take more time. All right, so as I mentioned before, these procedures are based on this table. So the standard here is 100 milligrams of water. So what we did was we're gonna assume solubility in terms of a higher temperature, and as we decrease the temperature, the solubility will also decrease. So that means it's going to be supersaturated, and that supersaturated is going to reverse solubility into building the crystal, right? And when the temperature is lowered slowly, the crystals become more of a crystalline structure, because these tiny forces are so small and very delicate that they need time to place each negative and positive ion in the correct position. So if you drastically decrease the temperature by putting it in ice, so straight from close to boiling temperature, putting it straight in cold water or iced water, then it's going to be the attractive forces are so small that they're going to be too bundled up, and it's going to end up making an amorphous solid. And you'll see that the crystalline and the amorphous solids are different. That's why in terms of the expensive crystals that we know, those crystals are made through a long time. That's why they're so expensive, because they allow the long periods of time to let each atom be into place and make those uniform looking structures called crystals that we buy. And it's the same concept with making the crystals with salt. So we want the temperature to be decreased very, very slowly, so each atom can be placed in the correct position. So these are the materials, and we're gonna use 98 grams of table salt. So we're just doubling this for each 200 milliliters of distilled water. And the reason we want to use distilled water is because distilled water is water that has been evaporated, so everything that's been dissolved in it will stay behind, and the pure water will be collected, and that pure water will be free from impurities. And again, you want your crystal to be as pure as possible, so having impurities such as other metals or any residue in your container can disrupt the structure and the uniform pattern of the atoms. Yeah, that's why you want your water distilled. And of course, that's why you also want a clean container and a clear one to see what's going on inside. And you want a piece of cardboard, string, pencil, or butter knife. Doesn't something straight like a piece of wood. So the first part is the nucleation, or making of the seed. This is the part where you make a little crystal that can build a bigger crystal off of. And see how you have the little atoms, and this is the liquid building up. And as you evaporate the water, or reduce the solubility, the ions or atoms will start to accumulate at a single spot, and that's when you can get your middle part of your crystal, and then a bigger crystal can be built off of that small part. So we're gonna pour 24.5 grams of sodium chloride into a petri dish or a shallow plate with rims. So you want something really shallow so you can evaporate easier and a little faster. And the reason why you want little is because with less you can evaporate a little faster, because you have less water to evaporate. So, and then that will be easier to obtain and tie or thread around and make a bigger crystal. So after you measured your 24.5 grams of sodium chloride, you will want to pour and mix 50 milliliters of water, and then you'll want to evaporate that very slowly by either heating it with your stove or a plate. And then once you evaporate the water, you'll collect the one crystal seed, and what you want to look for is the quality, and the quality will be determined by the size, clearness, and structure of the seed. So if it's very uniform all throughout, then you can use that one. If it's clear, then the clearer it is, then usually the less impure it is. And the size, so the bigger the size, the better results you're going to get, and the easier it's going to be to grow crystal. So once you get your crystal seed, you will want to tie a thread around it, and on the other side of the thread you will want to tie a pencil and make it about half the length of your container. And then with the cardboard you will want to make a hole that's big enough for the crystal seed to fit through it, and then you will have something that looks like this. And the cardboard will help stabilize the pencil. After making the crystal seed, you want to grab a larger container and pour 98 grams of salt in there and 100 milliliters of distilled water. Then you want to heat the solution close to boiling and mix it. And according to the chart, the salt should fully dissolve, and then once you put it in there, you want to let it cool a little and then put your crystal seed in there and let the solution cool slowly, and that's how you can get those perfect structures, those crystalline structures. And once you leave it there for a couple of days, don't leave it there for too long. Leave it for a couple of days, because if you leave it there for too long, then your crystal might partially dissolve. And so you will want to repeat the step because a few times, because only a small amount of salt will deposit onto your crystalline structure, because again your solubility level of salt doesn't really change too much. And that's why you have to be careful with loosening your crystal material when it gets too cold, because at that point the reverse process might occur, and instead of forming a salt, you'll start dissolving.
So I boiled some red cabbage water and divided them in 4 different jars. And so first I'm adding bleach to the first jar, and as you can see it turned into a yellow color. Then I'm adding water to the second jar, and this one's kind of hard to see, but it's like an indigo blue color. Then I'm adding vinegar into the third jar, and this one is like a red pink color. And then lastly I'm adding lemon juice to the last jar, and this one turns into a bright pink color. So as you can see, all of them change different colors, and this indicates different pH levels. So bleach was a yellow color, so that's our most basic, so a pH level of 11. Water was our neutral, so that's a pH of level 7. And then vinegar is like at a pH level of 2. And then most acidic would be our lemon juice. And so red cabbage was the pH indicator used in this experiment, and each and every one of them changed colors, so it was a good turnout.
This is the extraction of potassium carbonate from Banana's lab. I am Nick Nguyen and my partner is Vincent Pham. Potassium carbonate, or the compound K2CO3, is an alkali element. It combines with water to increase the pH. It was discovered by Sir Humphrey Davy in 1807. Bananas contain about 40% potassium when incorporated in soil, and potassium promotes movement of water and nutrients between cells. There are many applications of potassium. Such applications include: potassium supports plant growth and development. It supports plant utilization of water. It fights off diseases. It resists pests and produces more crops. Extracting potassium carbonate procedure. In the video, about 40 banana peels were collected. A brick oven was then set up, and the banana peels were then burnt until a powder form, or ash, was seen. Afterwards, a saturated calcium hydroxide solution was created, and then added to potassium carbonate. The solution was then slowly stirred, and after waiting 24 hours, 2 layers were formed and filtered to receive the pure potassium hydroxide. The chemical reaction can be seen below. Extracting potassium carbonate. Continue. Since we could not perform this lab experiment personally, these images are from the video in which the lab procedure is done. The image on the left is the banana peels being burnt in a brick oven until ashes form. The image on the right is the 2 solutions being filtered through a funnel in which the pure potassium hydroxide is collected in the beaker.
Hi, I'm Kirin Rodarte, and today I will be doing the slime experiment. You will need the following: a spoon, food coloring, corn flour, and a bowl. So this experiment is fairly easy. You will start by putting corn flour in the bowl. Okay, done. Then you will pour small amounts of water into the bowl until it forms a very thick paste. This is about the consistency it should be. So next you're gonna add your food coloring. You can make it to your preference. I'm gonna make mine's purple. Okay, done. It's a nice purple. So to demonstrate how the slime would work, you're gonna stir it very slowly. This should be pretty easy. As you can see, it's pretty easy. And then you're gonna try to do it very quickly. Hold on. As you can see, it's pretty difficult to do that. Part of the experiment, I will be punching our mixture. I will get back to you on how it went. Alrighty, so as you can tell, I left a little bit of an indent in there. However, I can verify that it did feel like punching a solid. Now, the explanation behind this is because most liquids have the viscosity of a liquid and most solids have the viscosity of a solid. However, corn flour slime is a special exception. The viscosity when no pressure is applied to it is almost like a liquid. As you can tell, when we were stirring it very slowly, it did move like a liquid. But when we applied a lot of pressure to it, the viscosity became denser. So it became more like a solid. And when you punched it, that's why it became incredibly hard. Now, there are other liquids that are the opposite of this mixture. For example, toothpaste. When toothpaste has less pressure applied to it, it becomes more liquidy.
pH indicator experiment by Taylor Newton. So for this experiment, you'll need red cabbage, distilled water, pot, strainer, measuring spoon, milk, vinegar, baking soda, lemon juice, beer, apple cider vinegar, and 6 cups, as well as a knife and a cutting board for chopping up the red cabbage. So for this experiment, you will bring 800 milliliters of distilled water to a boil, then add chopped red cabbage in, stir until you get the desired color of purple that you want, and then you can strain the water with the cabbage into a separate container, then place that container into an ice bath so that it can cool to room temperature faster. Then you're going to want to measure 1 teaspoon of milk, vinegar, baking soda, lemon juice, beer, and apple cider vinegar into separate cups. And also label those cups using a Sharpie of what solution it is. And then you're going to measure 1 teaspoon of the red cabbage water after it's cooled to room temperature into each of the 6 cups and record your observations. So this is my red cabbage solution. So red cabbage as a pH indicator. Phthalate is a pigment molecule found in red cabbage. This molecule is what will help you indicate whether a solution is acidic, alkaline, or neutral. So acidic solutions will turn the flavine a red color, neutral solutions will result in a purple color, and alkaline or basic solutions will become a greenish yellow color. So I've created this chart to tell you that what pH corresponds with the color. Here is before adding the pH indicator. You'll notice that the milk, vinegar, and baking soda are more of like a opaque appearance, and then the lemon juice, beer, and apple cider vinegar are a yellow appearance. So after adding the red cabbage as the pH indicator, you can see that milk became a light violet color, vinegar became a reddish pink color, the baking soda became a blue color, and the lemon juice became a red pink color as well. Beer was violet, and apple cider vinegar was also red or pink. So, as I mentioned before, milk was a violet color, meaning that its pH was 6 and it is a neutral solution. Vinegar was red pink, meaning it's acidic and has a pH of around 2. Baking soda is alkaline because it had a blue appearance, and that means its pH is around 7 or 8. Lemon juice is acidic because it had a red or pink color, meaning its pH is around 2. Beer had a neutral color because it was violet, and its pH is going to be around 6. Apple cider vinegar is going to be acidic, and it's around the pH of 2. Now, I did not have pH strips with me, so I could not actually tell what the pH of each solution was before or after. Those are just estimates.
The experiment for today is turmeric indicator. I hope you enjoy it. Materials you will need is lemon juice, soapy water, almond milk, turmeric, spoon, 3 glass bowls. Step 1. Take the turmeric powder and apply 3 spoonfuls onto the glass bowl. Step 2. Apply 1.5 cup of water and stir the bowl. Step 3. Pour the indicator onto the soapy water. Step 4. Pour the soapy water on the lemon juice bowl. Step 5. Apply the soapy water on the almond milk bowl. The purpose of this experiment was for you to use turmeric as an indicator to determine which substance is acid, basic, or neutral. I hope now you're able to do this on your own. Thank you.